So today we are going to start with a very short introduction of the Monte Carlo simulation procedure. It is actually a part of the mathematical modeling of part of your syllabus. That is mainly the unit 2 part of your syllabus. Okay, so mathematical modeling, but actually we mean by it, so suppose any realistic problem is there, okay, and we want to frame or design a model such that whenever the realistic problem or any experiment related to that problem is performed and a data set is created from there, say I name it as a D1, okay, then the data set can be approximated by another data set which is just generated via the model, mathematical modeling which we create. Okay, so basically, designing a mathematical model, or which is sometimes referred to the simulation of a mathematical model, is the basic task whenever we say about the mathematical modeling. Okay, mathematical modeling just deals with designing any model corresponding to any realistic or real life situation. Okay, for example, suppose we know about coin toss. Okay, so coin toss is what it is an experiment. Suppose you are provided with an unbiased coin and you toss it several times, so that what you get, either head or tail. So you just mark it, say head as 1 and tail as 0, something like that. So whenever you perform it, say 100 trials or 1,000 trials, no matter, it depends how many trials you perform, so you get a sequence of zeros and ones. That means a binary sequence. So this is how you are getting this binary sequence. You are performing the coin toss experiment. So this is a real life situation. Now suppose we do not have a coin. Instead we have a computing machine. Okay, what we want to do, we want to, so suppose we want to find out the result corresponding to 1,000 trials of the coin toss. That means if you have performed in original it is 1,000 trials. Now without the coin I want to simulate a data which is equivalent to approximately to the coin toss experiment 1,000 trials. Okay, so now what we will do, we can generate or we can write a suitable algorithm using some software in the computing machine. We can, and via using that algorithm we can generate a data set. Okay, say I name the data set as D2, and the original data set, whenever we are tossing the coin, it will be called the D1. Now we can say that the model which we have defined, or the algorithm which we have framed, is efficiently simulating the data set corresponding to the coin toss if D1 and D2 are approximately equal. That means given some specified range of accuracy, D1 is equal to D2. Okay, so this is what I gave a very simple example of what we do in mathematical modeling. Okay, so now, suppose I give an example where you can perform the experiment. That means if you have a coin, no matter if you can toss it. Okay, so there is nothing hard in it. But in some cases, the real life situation is so complicated that we cannot in originality perform the experiment as a whole or perform the experiment directly. Instead, what we can do, we can provide with some practical situation informations. Okay, so whenever we have the practical situation information, now how this mathematical modeling will be helpful in that case? See, whenever we are having some practical situation, some information is applied. Okay, then what we do, we again simulate an algorithm using those information related to the real life situation which we are facing as a problem. Then using some suitable computing machine, okay, we just run that algorithm and then generate a data set. Okay, now after we generate a data set, we have to check whether the data set which we are generating via the algorithm which we have framed is matching or is compatible with the information obtained from the real life complicated scenario. If it is matching, then okay, this is mathematical modeling is compatible with the situation, with the information which are related to the real life situation. If it is not, then we have to modify the model again. Okay, and even if it is, say suppose, okay, we are producing some mathematical modeling which is up to some accuracy, it is matching with the information provided with the in the real life situation, then one can try, given one algorithm, one can try to modify the algorithm so as to get a better algorithm which will give you very much more compatible result with corresponding to the real life situation. So this is mathematical modeling. See, we what we do actually, let us go into here. So model is actually what it can, you if you can just consider it. So suppose some inputs are given to the model, It is like just like an operator. Some inputs are given to the model, and depending on some algorithm run inside, which we design, okay, some outputs are obtained. So this is your data set which is generated. These are the inputs which will be applied to it depending on the situation which for which we are just creating the model. And once you get the data set, you have to verify with the real life situation problem. Okay, so now inside this model, that means inside this box, actually, as I said, there is algorithm. This is the main thing. And algorithm is often referred to as a simulation algorithm, because you are simulating some data set. Okay, so now when once we try to create or try to generate an algorithm, what we have to have some preliminary ideas about, we have to use some parameters. Okay, and those parameters and also some inputs. Okay, so see what we are doing, we are just generating a model for what, to tackle a real life situation. So for the real life situation only we can get the idea ki what will be the inputs to the model, and for the real life situation only we will have the idea ki what will the parameters which will be controlling the algorithm. So these are all the pieces of information which will be obtained for the scenario we are dealing with. Okay, this will be obtained for the real life situation only. So what is the difference? In real life situation, you have all those experimental apparatus, you have all these real life things which you can deal with and find out the result directly. But here we cannot have that thing. Okay, we have to just use this, design an algorithm and we just run it in a computing machine. Okay, so in short, we can say is some sort of virtual platform we are generating here. That is a real life situation is the actual platform, and this modeling is the virtual platform. Okay, so now once we are designing algorithm, as I said, the parameters and the inputs are there which are coming from the information provided, and then depending on whatever is our requirement, we set up some rules. Okay, that is actually we are trying to maintain the logical flow. This already you know ki whenever we are writing an algorithm, this is a basic structure ki we have to maintain the logical flow. Okay, and then once we run this algorithm in some suitable computing machine, a data set, I'm naming it as D2, is generated. Okay, so once this data set is generated, it is verified. That means it is cross-checked with the data set D1 arising in original situation, that means the actual situation. And as I said, if D1 is this algorithm is efficient, or we will call the algorithm is efficient if D1 is approximately equal to D2 up to a specified degree of accuracy. Okay, if not, then we have to modify the algorithm, we have to modify this part, we have to, maybe we have to use some more parameters. This depends on the problem which is given, and we have to modify or create some new algorithm. Okay, acha. Now one such algorithm, and it is very well known, that's why it is there in the syllabus, is the Monte Carlo simulation. Okay, in fact it is the probabilistic simulation algorithm. Okay, acha. For, as I said, it is a probabilistic simulation algorithm. That means what, it will be dealing with modeling or giving some algorithm where some random numbers will be generated. Okay, see, whenever we are saying probabilistic, that means there is a space of chance. We are not deterministically, we cannot say what will be the result. So definitely there is some randomness or uncertainty attached with it. Okay, so definitely when this Monte Carlo simulations basis is formed by the generation of random numbers. Okay, now how we generate the random numbers, there are some procedures, many, in fact there are many procedures. Up to your syllabus, two procedures will be discussed in the latter classes. Okay, so basic thing is that okay, Monte Carlo simulation deals with random number generations. Okay, so now Monte Carlo simulation is a probabilistic method, as I said. It is used as a part of the mathematical modeling to obviously tackle any real life problem which is given to us. Okay, now obviously there are some pros and cons of the this Monte Carlo simulation method. Acha. So this thing here is nothing. It is saying that whenever we are trying to see, not only Monte Carlo simulation, in this mathematical modeling, we are trying to actually learn some. Obviously, it is a huge part of analysis, mathematical analysis. We are learning, trying to learn some a few preliminary ideas. Okay, so there, if you are trying to learn a probabilistic simulation algorithm, obviously you should have some basic idea of probability and statistics. That is what they have said here. Okay. Okay. Now, some positive sides of the Monte Carlo simulation. Here, I have just enlisted it from the book itself. These are some of the positive sides of the Monte Carlo simulation, and also there are some negative sides. In short, let me just read it out so that we get a very rough idea about it. So when any Monte Carlo simulation is performed, random numbers are used, as I said. We will discuss about the some of the procedures. Okay. Achha. So here one example. This example, maybe if we get time, we will discuss it separately. Ki whenever, say, suppose you are throwing a dice, okay. So if you're throwing a die, that means that is a real life situation. You have a die with you, an unbiased die. You know ki there are 6 outputs related to it. So you throw the dice n number of times, okay. So in trials you perform. So that is the actual experiment you are performing. And as you know, ki each of the phase occurring is a mutually exclusive event. So obviously you will get if you mark 1, 2, 3, 4, 5, 6 as the 6 phases, so definitely there are 6 outputs possible. So now you see this is the real life situation you are getting. So up to 1 to 6, you are once you run the trials, you are getting a sequence having 6 elements, having 6 components. I'm not saying element, having 6 components. Each element has 6 components. So depending on that, whether you are getting 1, then in the first component you will have 1. If you are getting 2, then in the second component it will be 1, and remaining 0, and likewise. Okay. So here you are creating a sequence, whatever may be the pattern you follow, but you are creating a sequence depending on whatever output you are getting. Now you see, this experiment which you are running is a probabilistic experiment, because until and unless you throw the die, you do not know which phase will occur. So this type of experiment is a probabilistic situation. Okay. A probabilistic behavior, it is sometimes referred to as. Okay. So this is one situation. Now suppose I do not have the die, I cannot throw it, I do not know what will be the phase occurring. So instead what we do, I just take help of some algorithm, a probabilistic algorithm I take help of, and there the Monte Carlo simulation can be used so as to generate again a sequence of random numbers. Now you see, we are generating a sequence of sequence of numbers randomly. Why randomly? Because we are trying to match it with the probabilistic event. Okay. So somehow we are generating that sequence, and then we will be checking key whether this data set is matching with the original data set or not. Okay. So in that type of case, we will, if you do that topic, we will show how we use it. Okay. Now a principal advantage of Monte Carlo simulation is the relative ease with which it can sometimes be used to approximate very complex probabilistic systems. That I already said, real life situations can be easily tackled using this Monte Carlo simulation. That means, see, this type of advantage which they are mentioning here is a relative advantage. Okay, so until and unless we learn other simulation algorithms, okay, we have to take this as a fact. We have to accept this as a fact. We cannot compare. And up to your syllabus, we are going to learn only the Monte Carlo simulation. So up to whatever reason, we have to accept this. Okay, Monte Carlo simulation is an efficient algorithm, but we cannot just compare on our own, because we do not, till date, we do not know, or up to the syllabus, we cannot just consider other simulation algorithms. Okay. Now, additionally, Monte Carlo simulation provides performance estimation over a wide range of conditions rather than a very restricted range as often required by an analytical model. This is quite obvious. Whenever you do something analytically, there are some restrictions which has to be satisfied. Okay. Now, whenever we are just following Monte Carlo simulation, I am not saying ki no restriction will be there. Obviously, whenever you are designing an algorithm based on those restrictions only, the reasoning will come, the logical flow will come. Okay. So I'm not saying ki I will just relax all the restrictions, but what, I will relax some of them, or I will modify some of them, so that even if I modify, my results do not deviate from the original situation by a huge amount, does not deviate. Okay. So that much Monte Carlo simulation allow us. Okay. So actually, again I say ki I am just saying it out, but I cannot prove it, or rather I cannot justify by giving an example just now. Okay. So you just keep this in mind as a positive side of the Monte Carlo simulation only. Okay. Achha. Still, another advantage is that the modeler has control over the level of detail in a simulation. Okay, so obviously the Monte Carlo simulation, as they are designing, obviously the simulation algorithm which the user is creating. The user means you or me, whoever is creating the algorithm, they have a full control over the parameters. That means definitely over the logical flow. That means definitely whatever is going on inside, we can control it to a huge extent. Okay. Achha. And for example, a very long time frame can be compressed over a small time frame, or can be compressed, or a small time frame can be expanded, giving a great advantage over experimental models. Obviously, it's a huge time frame, it can be compressed to think as a short one, or vice versa. using this Monte Carlo simulation. And the most important thing is that this is compatible with many high-level simulation languages. These are some of the names of the simulation languages which can be used in a computing machine, such that the Monte Carlo simulation algorithm which we are designing can be run on those machines using this software. So this software compatibility of any algorithm is a huge factor. Okay, you are using an algorithm which is not at all compatible with the machine software you are using, then it's useless. Okay, so whenever we generate an algorithm, care should be taken ki okay, this is compatible with the prevailing or the available softwares in the market. Okay. Now, the negative sides of some of the negative sides is that the simulation models are typically expensive to develop and operate. Quite obviously, they may require many hours to construct and large amounts of computer time and memory to run. Okay, that means what you are using your computing machine along with some softwares installed in it so as to run a Monte Carlo simulation. But obviously, or you have some intuition, it is a probabilistic method definitely. So there is again this unpredictability there. That means, as I already said, it is based on random number generation. So you have to run many trials. So once we run many trials, whatever data is generated, which have to be cross-checked or which have to be used in some later steps, you have to store them. So that will cost time and also computer memory. So whoever has used this Monte Carlo simulation and wherever it is used in practical situation, this has been observed as a drawback of the Monte Carlo simulation. It takes a huge time, it takes a huge memory or engulfs a huge memory from the computing machine. Maybe we compare with some other simulation algorithm available in the market. Okay. Another thing is, another disadvantage is the probabilistic nature of the simulation model limits the conclusions that can be drawn from a particular run unless a sensitivity analysis is conducted. Okay, so probabilistic nature is itself a backlog of Monte Carlo simulation. As I always said, you are randomly generating numbers. Okay, so there is no pattern in it. What we are doing, we are randomly generating a large set. Maybe that large set is not entirely required, or maybe if we use a deterministic model, suppose we can use a deterministic model or deterministic algorithm, then we could have tackled the real life situation much more easily. But because we are using a probabilistic method, we have to run many trials. Okay, so that is the backlog of this Monte Carlo simulation. It is probabilistic in nature. Okay, so then we have to perform the sensitivity analysis. Okay, then definitely it is costly. So again, there is a question of timing and there is a question of memory and resource. Okay, it uses much more resource than any other efficient algorithm. Okay. Now, so these are some of the positive and negative sides. And then let me just, this is not only for the Monte Carlo, this is in general. As I said, we are just trying to learn the mathematical modeling. And as I said, its main task is to provide data to be checked, compatible, whether it's compatible or not with a given real life situation. So the real life situation can be of two types. Either it is deterministic in nature or it is probabilistic in nature, the real life situation. That means whether you are performing an experiment to related to a coin toss, it is a probabilistic in nature. And again, whether any particle is moving, so suppose under inverse square law, suppose, okay, you are trying to trace the locus of the particle. Okay, so that is a deterministic experiment. Okay, you know what will be, once you can solve it, you know what will be the path of the particle. Okay, so that is a deterministic, so suppose situation. Or maybe you can take another example. Suppose you want to find out the area enclosed by a curve y equal to fx. So there also, maybe it is complicated to find out, but it is a deterministic. If the area does not change, no external factors change, then definitely no matter how many times you measure the area, you should be getting the same thing. Okay, so this is a deterministic thing. Contrary to the coin toss, there it matters. Sometimes you are getting head, sometimes you are getting tail. So there is a probability attached to it. There is a game of chance attached to it. Okay, so these are the two types of real life behavior which can encounter, and simultaneously the model's behavior. So actual realistic situation behavior can be deterministic, can be indeterministic, and model's behavior can also be of two types, deterministic or indeterministic. Okay, for example, the Monte Carlo simulation is indeterministic method. Okay, now the thing is that key if the real life situation is deterministic, then it can be explained via a deterministic protocol, means the deterministic algorithm or deterministic model, or it can also be explained by a probabilistic model. Again, if the real life situation is probabilistic in nature, then also it can be modeled or it can be controlled by a deterministic algorithm or by a probabilistic algorithm. So this is the thing. Just I have listed it down here. Here, if it is deterministic, then this is deterministic. This is both of them deterministic is possible. Example: a model using the differential equations to trace or find the path of a particle moving under a force field, say constant force field or inverse coil or whatever. Okay. So these are some of the examples. Okay. Now, say the actual behavior is deterministic and model's behavior is probabilistic. So suppose you are trying to find out the area enclosed by a curve. As I said, it is deterministic. Okay, but we will see later. In fact, it is included in your syllabus. We can use Monte Carlo simulation to find out the area. Okay, so you are using a probabilistic model to get or to tackle a deterministic real life situation. And similarly, it can be probabilistic, and you are using a deterministic procedure to tackle the problem. For example, you are tossing a coin, so that is a probabilistic event, we know, but we can use a suitable approximate deterministic model to generate the data which we are getting in a coin toss experiment. So here the model, here the real life situation is probabilistic, but the model you are using is deterministic. Okay, so this is also possible. And the last one, both are probabilistic. That means the model, that is the real life situation is probabilistic, and the model or simulation algorithm which you are using to verify the data is also probabilistic. For example, tossing a coin experiment we are taking, and we are using the Monte Carlo simulation algorithm to just make it compatible with the data obtained in tossing the coin. Okay. So these are the things we are including in the introduction part of this mathematical modeling, and also the introduction of the Monte Carlo simulation method. Okay. So let us stop here.